Hi guys, last of the gas laws here. All right, so what's up with this? We've been talking this whole time about ideal gases. And ideal gases, if you remember, are ones that completely adhere to what is called the kinetic molecular theory. And the kinetic molecular theory has four basic ideas to it. The first of which is that the gas particles are always moving and colliding and doing those things. The second is that the gases are made of tremendously small atoms, or more to the point, there is a lot of space in between those atoms. It is also assumes that there are no intermolecular forces between the particles or the walls of the container. And it also assumes that as you go higher in temperature, they get more kinetic energy and they move faster. Now, if you have normal circumstances for a gas, then all four of those things are basically true or approximately true. But in the reality, two of those things are kind of lies. Which of these things really are lies? I'll give you a minute to think about that. Pause your video here and think about it. Which two of these things are lies? All right, hopefully you've unpaused now. And in reality, it's not so much that they're lies, it's just not entirely the truth, or can be adjusted in such a way that the truth is not quite the same. The first of which is this guy. The fact that we are ignoring the volume of the particles themselves, or we are assuming that there is a great deal of space in between those particles. If you have tremendously large molecules, or if you have a tremendously small space, then you might have a situation where there's not a lot of room in between those particles. And so that really could be adjusted in such a way to make it not quite true. This one here is also not true. We also know that there are intermolecular forces. Even in nonpolar molecules, there are London dispersion forces. So even in nonpolar molecules, there is some attractive forces between those guys. And so that's going to make it not quite true. So consequently, there are going to be effects of real gases or non-ideal conditions on the gases themselves that are going to manifest themselves in a variety of different ways. So that first one, like I said, is that gas particles actually do take up space. Now, in this picture, we are showing that there's lots of space in between the particles. But if we smush the volume down, now all of a sudden there is a lot less space in between those particles. So again, if you are talking about conditions of low volume, then all of a sudden this assumption is not quite as good anymore. This assumption that the particles take up no space or very little space is not quite true if we were to take all of those particles and smush them into just one corner. So if we were to take this whole box here and all of these particles and shove them into this, what do we got? 3, 6, 9, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If we were to smush the volume down to that size there, now all of a sudden, there is not a lot of room in between those particles. So again, that's not quite true. Additionally, gas particles actually do have intermolecular forces, and because they do have intermolecular attractions, they are going to, attract each other like tiny little magnets like we learned before, and that's going to have an effect on things as well. So, couple questions that the AP folks are going to ask you about this. First of all, what conditions make a gas non-ideal? Well, remember that if this is your pressure curve here, if this is your phase diagram, what makes a gas over here is a temperature that is very big, so again, temperature high, and a pressure that is very low. Here's your pressure that's low. That is smack dab in a vapor aspect of our phase diagram, and so you would expect a gas to behave like a gas. So what conditions are gases or vapors here? So gases are low pressure and high temperature. That's these dots over here, right? Those are the ones that tend to be the gases, the ones that are low pressure and high temperature, all right? So if it's supposed to not be a gas or a non-ideal gas, then the opposite is what makes it a non-ideal situation. So for instance, if I were to take this gas and increase the pressure on it, then all of a sudden it's going to turn into a liquid. And if it's going to turn into a liquid, then it's not a gas anymore, and it's not going to behave by the ideal gas laws. Or if I take a gas and I cool it down, it's going to turn into a liquid and then a solid, or if it's down here, it'll just crystallize straight into a solid deposition, right? So if I have a low temperature, then all of a sudden, then that is not going to be a gas anymore. That's going to be more of a solid. And so if it's a solid, it's not a gas, and it's not going to behave by the ideal gas law. So any conditions that are not gaseous conditions are the ones that are going to lead to non-ideality. So if you have high pressure and low temperature, high pressure and low temperature makes things non-ideal, because again, high pressure is up here. That's high pressure. That's a liquid and a solid. That's not a gas. And low temperature is down here. That's again liquids and solids down here. If you're at a low temperature, then that is not ideal either. So high pressure and low temperature are conditions which are going to lead to non-ideality, both of which, by the way, lead to a low volume. So if we were to pressurize this container, we could high pressure, low volume. Or if we were to cool this container down, then that would shrink the container and again make it a low volume. So you are talking about low volume, both of which are caused by high pressure and low temperature. Okay? Next, the other thing that makes it deviate from ideality are strong intermolecular forces. Remember, the stronger the intermolecular forces, the more those molecules attach together, and the more they attach together, the less space there is between them, and therefore the less gas-like they are. So here is water, H2O. Those guys have hydrogen bonds between them, and because they have hydrogen bonds between them, they are highly attractive. If you compare that to H2S, H2S does not have hydrogen bonds. It's barely polar, probably more nonpolar than it is anything, and so consequently, this guy here has low intermolecular forces. So this is low IMFs, and so it is going to behave more like a gas. This has high intermolecular forces. It's going to behave more like a solid or a liquid in there. Now there's an equation that goes along with this. It's called the van der Waals equation, and the van der Waals equation looks like this. It's just really PV equals nRT. You see that? So it's PV equals nRT, right? But what it does is it has these two factors here that correct for these non-ideal conditions. And those two factors are A and B here. These are the van der Waals constants, and these correct for the fact that there are attractive forces, intermolecular forces, and it corrects for the fact that there is actual volume of the molecules themselves. So this A factor here corrects for the fact that there are intermolecular forces, and this B factor here corrects for the fact that the molecules actually take up space. Now, if you were so interested, you could look these up, and the A values and the B values for different substances are there, right? But you're never going to have to do math with these guys. Just a couple of things to note. Water is a particularly small substance, but look, it has a very high A value as compared to other substances that are of similar size to it, because water is extremely polar, right? So that kind of things. But guys, you're not ever going to have to do any math with any of this, so I'm going to skip this and not really talk so much about this, right, as far as the math is concerned. But what they are going to ask you about is they're going to ask you conceptual ideas about this. And the conceptual ideas about this are as follows. The real effects of non-ideality can be seen because of the fact that they actually take up space and they actually have intermolecular forces. And you can see them in two ways. All right, so if you have molecules that are large, So these are larger molecules. These are the ones that have a high B value over here because they actually take up space in the substance, right? So if you have a large molecule, then what that means is that you are either going to see an increase in either the volume or the pressure, depending on which one that you are holding constant. So if you are holding the volume constant, you have a rigid container, then you're going to expect to see a higher pressure than you would expect because the real gas deviates from the ideal gas a little bit. So you're going to see a larger pressure than you would expect because those molecules are actually taking up space. Or if you are keeping the pressure constant, then you will see a larger volume for the substance. The volume will go up. The balloon will be bigger than you expect because, again, those particles actually take up space. So if you are comparing two different substances, whichever molecule is larger will deviate more from ideality, and it will have either an increased volume or increased pressure, as the case may be. All right. The other factor is the intermolecular forces. And because the intermolecular forces, because these particles might actually attract each other, that means they squishify in a little bit. And if they squishify in a little bit and are magnetically attracted to each other, then you are going to see a decrease in the volume or the pressure because of that, because they have higher intermolecular forces. So if you have high intermolecular forces, you will see a lower volume or a lower pressure than expected because those particles have attracted to each other in there. So if you have big molecules, right? Big molecules tend to have an increase of the volume or an increase in the pressure. Highly attractive molecules tend to have a decrease in the volume or a decrease in the pressure because of their intermolecular